Hi, I'm Bryant. Thanks for joining me in the second video in a three-part series on building an AI application using AI. Insights and Actions is a personal project where I set out to see if I could build an AI assistant slash CRM tool using just AI prompts in 8 weekends, so 16 days. And although the application is just for personal use, I learned a lot along the way, and I wanted to share what I learned during the process so that other people could benefit from my experience. The third video will be dedicated to lessons learned. In the first video, which if you haven't seen, I would recommend that you watch before this, is where I talked about the what by walking through some of the application's features along with the project's overall goals and constraints. Today, I'm going to talk, I'm going to explain how it actually works under the hood. Not every corner of the code base because it's pretty big, but the main systems that matter. So how requests are processed, how routing works, how agents coordinate, how data is stored, how the vision system plugs into all of this, and the specific technology used to get it done. By the end, you should have a clear mental model of the architecture, understand how a single message turns into a combination of database lookups, API calls, agent outputs, and finally, a clean response in the UI. So first, let's take a look back at the 4 rules that I gave myself for the project, just to ground it. 1, it had to run locally, so no subscriptions, no cloud dependencies, no sensitive data leaving my computer. 2, AI had to help build every part of it. Codex and Claude were my development partners, and my only tools were prompts. 3, it had to work the way that I work, and that meant not just a chat interface. I needed to handle voice conversation and provide keyboard shortcuts to use triggers for tasks that weren't really suited for chat. And it also needed to work across multiple data sets. Some of the data was going to be on my machine locally, some would live in the cloud, and some was only accessible through a VPN. So I needed to be able to choose which data sets the assistant used at any given time. At a high level, Insights in Action follows a consistent pattern every time something happens. Router, coordinator, agents, aggregator, UI widgets. So no matter which feature you're using, drafting an email, checking your calendar, summarizing news about a company, or just asking who showed up at the house today, it flows through that same pattern. On top of the core engine, there are multiple user interfaces. So there's the main web chat single page application. There's also the enablement role play interface, the journal notes view, and the vision monitor. And finally, there's a Chrome extension that can put data into the system. But they all talk to the same Express.js backend. So from the system's point of view, it doesn't really care how a message arrived. Everything goes to the same place. So what happens when you hit enter? Well, when you send a message, the system doesn't immediately fire a large language model. It follows a process that begins with the router. And the router is the decision maker of the entire system. Its job is to decide what the user is really asking for and which agents should be involved and whether the system needs retrieval or it can answer directly. And it does this in 6 stages designed to be predictable and resistant to hallucinations. So level 0 is triggers. This is the first layer and it's just pattern matching. If the input matches a known pattern, say a greeting or a quick response that's been entered into the admin tool, then the router can respond directly and take a fixed action. This layer runs in about a millisecond and it doesn't touch the LLM at all. Level 1 is router cache. So the same way, if the same or a very similar query was seen recently within 5 minutes is the default, the router uses a cache. And it can reuse the previous routing decision instantly, including which agents it ran and what parameters. So this is particularly useful in the enablement role plays and repeated workflows where users tend to ask slightly different versions of the same question. Level 2 is the example retrieval. So the system looks up a small set of similar examples from a curated set of routing training data. These examples represent past queries and the correct agents and parameters for those. They're fed into the model as context so that classification is consistent over time, instead of changing its mind on every small wording variation. So level 3 is where we use the smaller, faster Llama 3.2 model, and it receives the user's query, the retrieved examples and descriptions of all the available agents and their parameter schemas, and the output is structured JSON that specifies which agents to run, their confidence scores, and any parameters extracted from the text. To keep this safe and predictable, the system uses instructor.js with Zod schemas. Instead of hoping the model returns valid JSON, the schema defines exactly what the output must look like. And if the model returns something invalid, it's automatically retried until the response conforms. That means no more random keys, no malformed JSON, and far fewer routing surprises. Level 4, once the classification is done, the router filters out any agents whose confidence score is below a certain threshold. So agents above 0.7 are treated as strong candidates. Agents in the 0.3 to 0.7 range might be included as secondary, and anything below 0.3 is disregarded. And this keeps the system from firing off agents based on weak guesses. And then finally, level 5 is if nothing passes the threshold, or if the query is clearly asking for information rather than an operation, the router falls back to a retrieval flow using the knowledge agent. The query is embedded, quadrant and local databases are searched, and the top results are collected, and the larger LLM synthesizes a response using those documents. This guarantees that even unclassified queries still get a meaningful answer. Once the router decides which agents should run, the coordinator is responsible for orchestrating them. The key idea is that agents don't call each other directly. Instead, the coordinator builds an internal dependency map and executes agents in waves. Wave 1 contains independent agents, ones that can run immediately without needing data from other agents. And this usually includes things like the calendar agent, contact agent, weather agent. These run in parallel, so the system can fetch calendar events or contact details all at the same time. Wave 2 and later waves consist of agents that depend on the outputs of earlier ones. So a good example is an email agent. It may need the time and subject of a meeting from the calendar agent and an email address from the contact agent. The coordinator waits for those upstream agents to finish, passes the relevant data along, and then only executes the email agent once it has all the information it needs. This wave-based execution model is what lets the system stay fast while still respecting dependencies. So after all the selected agents have finished, their outputs are passed to the aggregator. This component's job is to turn a collection of partial results into a single coherent response that the user sees in the UI. In the simplest case, where only one agent was needed, say only a calendar agent, the aggregator doesn't need to do very much. It can return the agent's data directly as text, plus a widget that the front end will render as an event card. For more complex queries involving multiple agents, the aggregator uses the larger model, Llama 3.3. It provides the raw agent outputs, some instructions about how to combine them, and any relevant context from the conversation. The model then synthesizes a unified answer in a natural language, and this prevents the user from seeing several disjointed chunks and instead gives them one clear explanation. The aggregator is also where special behaviors live, things like brand voice rewriting, content revision, or sending back a widget-only response for email drafts, where the structure matters more than the narration. Now, to avoid the classic wall of text problem you get with just text-based chats, Insights in Action uses a widget-based response model. So agents don't generate HTML or layout. They simply return a widget type and structured data, and the front end takes care of the rendering. There are widgets for email drafts, calendar events, contact cards, sports schedules, battle cards, quizzes, mind maps, just about everything. Each widget type has a template. It's stored in the SQLite database, and the front end fetches those templates and merges in the agent data to produce a consistent styled component. This makes the assistant's response feel much more like a real application and much less like a raw chat feed. And you can skim, click, and act on the information within those widgets without having to digging through paragraphs of information. So underneath the routing and agents, the system relies on a hybrid data layer, a relational storage in SQLite, semantic search in Quadrant, and a set of local JSON vector datasets. SQLite holds all of the strongly structured data, like contacts, company events, user profiles, etc. One of the key tables is the content items table, which unifies the RSS items, the news stories, Reddit posts, and the monitoring updates all under a single schema. And that makes it easy to query everything related to a given company or a given topic without caring where it originally came from. The Quadrant Cloud serves as the vector database. It stores 1024 dimensional embeddings from the Nomic embedded text model for documentation, notes, monitoring updates, news, etc. And whenever the system needs to answer a question based on unstructured content, it queries one or more of these collections. And on top of that, there are local JSON vector databases acting as offline knowledge packs. These are used for data that I don't want to leave my own system. I don't want to put in the cloud. And they use the same embedding format, but they live locally and they can be toggled on and off in the interface. On the back end, Insights and Actions runs on Node.js with Express handling, HTTP routing, SQLite for databases because it's fast and synchronous access and keeps the code straightforward. Quadrant is accessed through its REST client, and Instructor.js with Zod enforces structured JSON for all the LLM calls. The front-end app is an ES6 module single-page application. Different modules manage things like chat, enablement, mind maps, data sets, admin tools. Socket.io is used for real-time updates, so long-running operations can stream back results without blocking the UI. And the system also integrates with both Google services like Calendar and Drive and Gmail, and with native Mac OS applications, Calendar, Mail, Messages, Reminders, and a number of external APIs like the News API, Serper, and OpenAI Vision is used to handle extracting content from images. So in addition to the text and tabular data, Insights and Actions includes a vision subsystem that can analyze images from a live camera. Node orchestrates this work as well, but Python does the heavy lifting. The vision stack uses OpenCV and Pillow for preprocessing, YOLO V8 for object detection, face recognition and deep face for facial analysis, and RoboFlow models for vehicle and object recognition. Results are stored in the detections database, and once the data is stored, the monitor agent can send alerts, or it can answer natural language questions like, who came by the house today? Were there any unknown cars in their driveway? Anything like that. But to see this in action and understand it the best, let me give you an example that we can just walk through. So let's say for the Total Guide website, we want to look at a competitor of ours and get an update of where we stand. So we'll enter into the chat, give me a competitive snapshot for company X, and the message enters through the chat UI. It passes validation and trigger checks, and it doesn't match a simple trigger, so it reaches the router. The router determines it needs company agent, company events agent, monitor agent, company research agent, and contact agent. In wave one, all the data gathering agents run in parallel. Company agent pulls the feature comparison matrix and a company profile. This is updated monthly via a cron job for each tracked competitor we have. A company events agent fetches recent news and Reddit discussions and any tracked events involving the company, so conferences, product launches, etc. Monitor agent grabs RSS feeds, blog posts, and customer sentiment. The company research agent pulls from SEC filings if it's a public company, plus hiring trends based on job postings. And then the content agent pulls in relevant information for any tracked contacts that we have within that company. In wave two, once all the data is collected, the aggregator synthesizes everything using Llama 3.3. It builds a unified competitive intelligence view. The result is a competitor snapshot widget with expandable sections feature by feature comparisons against the company that we chose, a news timeline, Reddit and community sentiment, financial metrics, hiring velocity, tracked events involving the company, contacts we know there, and an overall competitive positioning summary. So this is an inter-agent communication at scale. 5 agents running in parallel, sharing context through the coordinator's dependency graph, all synthesized into one actionable view.